Early in the 20th century, around the 1920s, researchers developed what is now called quantum mechanics, which is a description of our natural world at a very, very small scale. You could ask, okay, how small? Well, we're talking about atoms, neutrons, protons, electrons. And this first quantum revolution, as we now call it, was how we began to understand the way that atoms work and how they assemble together to make the reality that we see around us today. And that led to an information processing revolution that we saw in the 20th century. But what we've learned over the last 100 years is that these properties of atoms or quantum mechanical objects need not reside only at the very small scale. Now we're in an era that we call quantum 2.0, where we're now using the quantum mechanics to engineer and build systems at a much larger scale, even macroscopic scale, even something we can see with our eyes. And by doing this, we can take advantage of these quantum mechanical properties, not just at the atomic scale, but at a chip level scale. And we can even build things like quantum computers with them.
Quantum mechanical properties. What do we mean by that? What we're really trying to do is describe what's happening at the smallest scales of our universe. It turns out that if you try to use the physics and mathematics of our classical world, say how do planets move around the sun or billiard balls bounce on a pool table, that math breaks down when we go to describe how do atoms interact with one another, or how does an electron move around the nucleus of an atom, and we need to use something different, which we call quantum mechanics.
To understand what makes a quantum computer powerful, I find it useful to compare to our conventional transistor-based computers that we have today, like laptops. If you have transistors in a computer, they represent digital zeros and ones, but each transistor can only represent one of them at a time. It's a zero or it's a one, that's it. If I, instead of transistors, go to my quantum computer, I now have quantum bits or qubits. And qubits can also represent digital zero or digital one, but importantly, they can also represent superpositions of zero and one simultaneously. And the way that we think about this is in terms of the planet Earth, where the North Pole is state zero and the South Pole is state one. And if you're a transistor, you can only be at the North Pole or the South Pole. But qubits, like humans, can be anywhere on the surface of the planet Earth. And when we're anywhere other than the North or South Pole on the surface of the planet Earth, we are in a quantum superposition of 0 and 1 simultaneously. In a quantum computer, when we process information, we're manipulating all of those possible aspects simultaneously. And this is what we call quantum parallelism. In addition, those quantum states quantum mechanically interfere with one another, just like water waves can interfere on the surface of a pond. And it's a combination of quantum interference and quantum parallelism that gives quantum computers their power, enhancing the right answers while suppressing the wrong answers.
Quantum interference sounds exotic, but you experience it all the time in the classical world. These scribbles behind me here are actually trying to illustrate what happens when two sound waves interfere with one another. So you can imagine there's two speakers here, and these curves are sound waves emanating from them. And then at the points where they overlap, these circles here are points of interference. So depending on where you're sitting in this room, you might experience sound that is louder or quieter. In quantum mechanics, particles also have something called a quantum mechanical wave function. And this thing can operate in a similar way, where depending on how those states overlap with one another, you can get interference. In quantum computing, we're using quantum interference to our advantage so that at the end of an algorithm, we use constructive interference to amplify the right answer.
So we do have quantum computers today. We're still learning how to build them, and we're still learning how to use them. But the promise is that quantum computers could, for certain problems, vastly outperform what we can do with our conventional computers. Here at MIT, we cover all aspects of quantum, from algorithms and the design of those algorithms that we would run on quantum computers, to developing these various hardware platforms that we would use to realize quantum computers. These include the superconducting, semiconducting, neutral atom, and trapped ion platforms. Interdisciplinarity thrives at MIT, and it's very important for technologies like quantum. And the reason is that as we build quantum technologies, we need to draw on information from different expertise in different domains. And fortunately for us, we have all of that expertise right here in-house.